Hello students, welcome back to the Tantray physics classes. Today's lecture is again on gravitation, but today I will tell you something about the geostationary satellite. First of all, let us explain what is the geostationary satellite. Geostationary satellite is a satellite which is at rest with respect to Earth. It moves, but with respect to Earth, it seems to be stationary. That's all. And this geostationary satellite is generally used on the equatorial plane of the Earth. Something like this. It is Earth, and its radius is r, mass is m, and it is the equatorial plane, let me suppose. It is the equatorial plane, and the satellite is revolving in this equatorial plane around the Earth. And its time period is, it is a circular orbit. When it's moving in the equatorial plane, it is a circular orbit. And it is something like this. Earth is like this, and the satellite is moving on the equatorial plane, right? But it is moving in a circle. Let's make it a circular path so that we can understand. It is Earth, mass is m, and it is a satellite here moving around the Earth with orbital velocity v0 and at a distance r. This satellite of mass m, it remains stationary with respect to Earth. How is that possible? How can it remain stationary with respect to Earth so that from the Earth it remains fixed in the space? For the Earth, it is moving, but for the Earth it remains fixed in space. That I want to explain it like this. Okay, let me first explain how it remains fixed. So what are the conditions that it remains fixed with respect to Earth? See here, it is Earth. Suppose it is some place on the Earth, and it is a satellite here, right? Now, satellite moves like this, and Earth also moves around its own axis in 24 hours. Satellite is here, and the Earth's position goes over to here, this position goes over here, and the satellite is here, and the position on the Earth goes over here. Any place, fixed place, goes over here, and satellite is here, the position on the Earth goes over here, and satellite moves in a circle. The Earth also has rotated its own full cycle. So that means if the time period of this satellite around the Earth is 24 hours, the same as the time period of the Earth around its own axis 24 hours, it will remain stationary with respect to Earth. It will be fixed. Hypothetically, if you are here, you see the satellite just above your head, you will always see the satellite above your head. Always see the satellite above your head, because you are rotating and the Earth satellite is also moving in a circle, and both remain fixed with respect to each other. So that's the concept. The concept is, if the time period of a satellite around the Earth moving in an equatorial plane is 24 hours, the satellite remains fixed with respect to the Earth. That is what we mean by geostationary satellite. Geostationary. Geo means Earth, stationary. It remains stationary with respect to the Earth. But now the point is, what is this time period of the Earth, of the satellite around the Earth? That's 24 hours. Its frequency is the same as the frequency of the Earth about its own axis. Its angular frequency should be the same as the angular frequency of the Earth about its own axis. That's all. But now, at what height we have to launch it so that it has time period the same as 24 hours? Because at different positions, at different heights, it will have different time periods. We have to fix its position in space so that it has the same time period as 24 hours or as that of the Earth. That's all. So, first of all, I should write certain points here which you remember for the geostationary satellite. First point is that the time period of the satellite around the Earth is 24 hours. Time period is equal to 24 hours. T is equal to 24 for the satellite. For the satellite. Number second, frequency. How many revolutions it makes around the Earth? Frequency. same as that of Earth. Same as Earth. Earth around axis. Earth. But that's quite obvious. That's obvious. And time period is the same. When time period is the same, f is equal to 1 by t. It should be the same. 3 omega is equal to 2 pi by t. Should be the same. Same for Earth and same for Earth and the satellite. But this is time period of the Earth, time period of the satellite around the Earth, 24 hours. It is the same as the time period of the Earth about its own axis, making day and night 24 hours. The frequency of the satellite, the same as the frequency of the Earth about its own axis. Omega also the same, angular frequency, which we call as omega is angular frequency, same for the Earth and the satellite. Okay? Now, what is its use? Geostationary satellites are used for communication applications, intercontinental communications. When you want to send the signal from here, from India to United States, use from one part of the world to the other part of the world, you have to send it into the space. The geostationary satellite receives the signal and sends it back on the Earth at some different place. So, geostationary satellites are used for intercontinental communication applications. Right? Now, let me go to a different point. The point is, at what height this geostationary satellite should be launched so that it has the same time period as that of the Earth. Because at different positions, time period of the satellites are different. So, we have to have the particular position so that its time period is the same as that of the Earth, that's 24 hours. So, how to do it? It moves in a circle. So, what is the equation that I am going to write? Obviously, the centripetal force is given by the gravitational force, that is capital M, small m by r square. Centripetal force on this satellite is provided by the gravitational force, right? 1 r gets cancelled, m gets cancelled, and we write V0 square is equal to gm by r. Now, what is orbital velocity? Orbital velocity is, if it makes a circular orbit, the orbital velocity can be written as 2 pi r, circumferential distance, by time period. Circumferential distance 2 pi r by time period whole square is equal to gm by r. So you can write it 4 pi square r square by t square is equal to gm by r. Now you cross multiply it. And then you get what is r, the radius of the orbit. The radius of the orbit, I want to know. Radius of the orbit. How to find the radius of the orbit? So it is 4 pi square r cube is equal to gm t square. Now r cube equal to gm by 4 pi square t square. Now what about r? Orbital radius of the satellite. How much away it is from the center of the Earth? How much away this satellite is away from the center of the Earth? How to find that? So it is r equal to gm by 4r square t square whole raised to power 1 by 3. So r equal to orbital radius of the geostationary satellite. If I substitute all the values, gm, t, 4 pi square, t you know 24 hours. If I substitute them, I will get 36000 and 6400. That is 004, 2 and 4 kilometers. At this distance, it should be kept away from the center of the Earth. It should be launched at this distance from the center of the Earth so that it becomes geostationary. At any other distance, that it will not be geostationary because its time period will not be 24 hours fixed. Its time period will be different. if you launch it at a different position, maybe closer than this or away than this. Okay, but how much away it is from the surface of the Earth? Because here it is r. How much away it is from the surface of the Earth? This small r is r plus h. That is 42400 kilometers. And h is equal to 42400 minus r. That is 6,400 kilometers. So what is h? At what height it should be launched? At what height it should be launched from the surface of the Earth? That is 36000 kilometers. So all the satellites which are to be stationary with respect to Earth had to be launched at a height of 36,000 kilometers away from the surface of the Earth, and then they become geostationary. This was a lecture on geostationary satellite, and the next lecture will be on Kepler's laws. Keep on watching the lectures on YouTube, and don't forget to download the app, Tantray Physics Class. Thank you.